Now it's flatter.
And
Yes.
Will it go in the opposite direction?
Opposite direction, like.
Flip below?
No, it just stretches.
Oh no, well, because it's multiplying it by 0.99 each time.
Yeah.
So it's going to have like a logarithmic decline. But I think we just hit the point where the bottom and top are approximately the same spot. We could use an if statement on there. I'm not sure how exactly though. Maybe we'll just set that to flatten really slowly. Dot x. Dot z. Okay. Now it will slowly get very flat. What did I say wrong? Oh, there. And wide. Should get wider, I think.
Yeah.
Yeah, it's getting wider. Right. It's good to have it change. Oh, I guess I should start talking about things.
I already started recording a little while ago.
Oh, okay, okay. You got the whole flatter and wider and longer part of this thing. Okay, so this time we'll talk about compute shaders. So these are kind of the last big type of Lego to pull out of the box here. Then we'll have all the pieces, and we can do whatever we need to. So the compute shaders allow you to actually change stuff in GPU memory and have kind of a general purpose program. This one, of course, still does 3D rendering and that kind of thing. And that's one of the main reasons to use a compute shader. Now, you could actually fire up OpenGL and use a compute shader to do a completely general purpose calculation that has nothing to do with 3D graphics at all. Kind of the way we actually did that with the Vertex shader and transform feedback a couple weeks ago. But that's not the main reason that they exist. Main reason they exist, you can use something like OpenCL along with OpenGL. There's actually an interface there that will allow you to use those two together. But OpenCL is a different framework. And so usually when you involve two different frameworks that can talk to each other, it makes everything get a lot more than twice as complicated. And so there's a certain motivation to avoid it in favor of a simple kind of OpenGL model-based framework to do computation that's related to graphics, but doesn't necessarily fit into the regular graphics pipeline. So that's where compute shaders come about. So this compute shader that I'm using here is actually a separate program. So the rendering loop on this program here has a compute shader that's run right up here, GL dispatch compute, and that changes the vertex locations before we go through and do the regular set of things and eventually run GL draw elements like we've always been doing. So there's a separate program here. We GL use program like before, but we also have a computational program that computes stuff ahead of time before we go into the regular loop. So if we look at our rendering pipeline.
I have a dumb question.
Sure.
Could you write an overly complex calculator that runs entirely on the graphics card?
Oh, for sure. Yeah.
Using these?
Yeah. Now, the other thing about doing it with a calculator, so if you have like a pocket calculator interface, like the Windows calculator or something that you can click on buttons and compute things, sure, that would work. It would be a little bit hard to set it up to use more than one GPU core because mostly you have one arithmetic operation at a time with those. So it would be somewhat slower than doing it on the CPU. The GPU operates at a lower frequency, and of course you got to run things out to GPU memory and then do the computation and bring it back. But sure, you can do it.
Would be extra ironic because then if the calculator interface was software rendered.
There you go.
Yes.
That's right.
Make a completely backwards calculator.
Yeah. So we got the rendering pipeline. We talked about all these types of shaders. The compute shaders are actually outside the pipeline. They're in this particular case that I set up here, it happens before the pipeline. So like right up here. But you don't have to even have the regular pipeline. You can just run a compute shader all by itself. No problem there. That gives them a bit of flexibility. Now, what you don't get to do with the compute shader that Jesse, who's not here, wanted to do is just go ahead and stick it somewhere in there, like, oh, and at this point we have the compute shader, but it doesn't let you do that. That's not the way. Okay, so it exists outside the pipeline. It's not like an insertable extra step or something like that. Okay, so since it doesn't operate in here, in the pipeline, most of these stages all have some defined input. You know, when you get to the fragment shader, the pipeline has done rasterization, and so you've got fragments, and the fragment shader is invoked once per fragment. You might be able to set up multiple invocations on it, but anyway, the fragments that you have dictate how often it's run. Same thing with the vertex shader. You've got a certain number of vertices. Sure, you can have 2 invocations per vertex or 100 invocations per vertex or something like that. But each vertex defines one thing that it ought to do. And sometimes there's not really, you know, there's expansions and whatnot. The tessellation shaders expanded into a whole bunch more things, but there's always some notion of how many times the shader ought to run. With a compute shader, since it's outside the pipeline, there's really no such thing. And so, because of that, they operate in this abstract compute space. So the abstract compute space for compute shaders is a 3D grid of what they call work groups. And a work group is kind of what we have with the regular shaders. So if you think about it in pipeline terms, the work group for a geometry shader is all the primitives. You get 1 work group per primitive. With the vertex shader, you get 1 work group per vertex. So that's kind of what a work group is. And we don't use the work group term in the rest of the pipeline, but it pervades the compute shader. So you think of one kind of, when vertex is 1 work group for a vertex shader. For a compute shader, we really get to define what the work groups are all by ourselves and kind of make it up. So that's what you have. Now, with a vertex shader, it's talking about how 1 work group is like 1 vertex that it vertex shades, but you can have more than 1 instance for that vertex. And you can do the same thing if you want to for a compute shader. And so, besides just being able to have multiple instances per work group, your instances are actually a 3D grid themselves. Oh. And so you have instances that are divided into 3D space. So your instances have an X, Y, and a Z coordinate. So with a vertex shader, you have work groups defined by which vertices you have, and then you have a kind of a linear 1D array of instances. Here you have a 3D array of instances for each work group, and you've got a 3D array of work groups. So that gives you quite a grid-based setup.
Is that a good thing?
Well, if your computation can be visualized as a 3D grid of tasks that each require a 3D grid of instances, then it's absolutely perfect. If your computation is somewhat less complicated than that, it still works pretty well. You just have to ignore. You can either ignore 1 3D grid or the other. You can define it and say, okay, there's just 1 work group, but it has instances in this 3D grid. Or you can say we've got a 3D grid of work groups that have exactly 1 instance each. Either way is fine. And then you can actually ignore some of the dimensions. You can say, okay, our 3D grid of work groups consists of a space that has an X dimension of 100 and a Y dimension of 1 and a Z dimension of 1. So then you define a row of 100. And so you can say, this is my work groups. And each of the work groups has exactly 1 instance. So now you've just got 100 invocations of this thing total. And they're numbered 0 through 99 by their X coordinate.
And then work groups don't run at the same time as each other?
They don't have to.
Okay.
There's not really an order guarantee here. You can use synchronization primitives if you need to. And actually this example has one, but I think if I take it out, it still happens to work okay. Okay, so you got these 3D grids and whatnot. So if you really didn't want to have a 3D grid of 3D grids, you just have to pick some things to ignore. Just set to 1. And then it's okay. Okay, as far as storage. So for storage on these things, the inputs and outputs are really not nearly as rigidly defined as any of the other stages. You know, the geometry shader, you're getting in a primitive, and that's what you deal with. Here, there's nothing like that. It does have some built-in inputs that define where you are in the abstract compute space and how big the abstract compute space is. So you can find out which work group you're in and which instance within that work group you're in 3D coordinates. But for the rest of the input and output, you have to figure it out. So you end up needing storage for each of these shaders. And so there's shader storage buffers that are really kind of perfect for that. They're available with OpenGL at the same point compute shaders are. And it gives you this kind of in-out parameter we've been wanting. This vertex feedback, I think everyone was kind of hoping that you'd just be able to modify the vertex locations. And that's not what the vertex feedback does. It captures what was rendered in part of the pipeline in a separate buffer, and you can use that buffer as the input later if you want to, but it doesn't really give you like a modifiable buffer. With this, you get a modifiable buffer.
Wait, what was that?
So with the feedback, the feedback, you can pull it out at some point in the pipeline, but it kind of comes out at some point in the pipeline. So if you want to capture what the geometry shader did, for example, you can do that. You set up translation feedback, and you get to capture whatever came from the geometry shader. But it is recording that into a separate buffer that you can then use as the input for the pipeline if you want to.
Couldn't I do that for the hairs?
Yeah, you could. So that can work like that, but it is recording something into a separate buffer that you can then decide to use as input, which is different than having a buffer where you can just plain modify the contents. With the compute shader, if you use a shader storage buffer, you can have a buffer where you can just plain modify the contents, like a normal array, except in the GPU memory, of course. Okay, so that's what the shader storage buffer is. It's something you can actually go ahead and modify. Oh yeah, I came up with this question while I was writing the notes, and I didn't have time to write a little test program to answer this question. Can we use one from a vertex shader? I think the answer is probably no, but I haven't checked. If you know, feel free to ask. Anyway, so that's this is the in-out one. So it's declared as a buffer. We do have to explain the layout when we do this. Let me show you how this example works. I was going to talk about this example down here, but I think I should pull up the example as part of this. I think it's getting to the point where it's too many random little things to remember. Okay, so the example, well, now it flattens this thing out. That's not what I used to do, but it does that now. So that's fine. So let's look at the compute shader real quick. So there's not really a standard extension for these things. I've seen some people name their compute shader like .cs for .compute shader. That slightly bugs me because that's the same extension used for C# files a lot of times. So I called mine the .c.glsl, keeping that. I think .compute might be another possibility that's sometimes used. Anyway, it's not really a standard, and there's maybe 3 different common conventions. There may be more than that. Some people like to put all the shaders in the same file because they're all short. Sometimes. Okay, so here's a compute shader. So we have to declare some layout specifications here. So there's a few different options for layout on this buffer, but the basic thing we do is we have this buffer chord 3D, and it's very much like the chord 3D we've been talking about so far with the vertices. In fact, it's the same chord 3D. If we look at cube.cpp, I keep modifying this cube demo for every last thing. We've got the vertices. I went ahead and added the last piece to this just because I was having trouble with the vec3. I'll tell you a little more about that later. And so it's almost the same. Now, when we GL bind buffers, the cube color is untouched, the same as the original demo. So instead of binding it as a GL array buffer, we go ahead and bind it as a GL shader storage buffer. Shader storage buffers are the flexibility that you can change them. And they also have a higher maximum limit. I think the array buffers, the implementation is required to guarantee that they can be at least 16 kilobytes, which is really not very big. I think most implementations in actuality let them be a lot bigger than that. But the shader storage buffers are required to be able to be at least 128 megabytes. And most of the time, you can declare one up to the limit of your card memory if you want to. So if you want to do some computation, you don't care about graphics, you have a 4 gigabyte card, you should be able to have close to 4 gigabytes in your shader storage buffer.
So can you use it in the other shaders?
Yes, you can.
Wait,
So,
you can change it in the compute shader?
yeah. So this buffer up here, this cube vertices buffer, is made just like it was before, except that it's declared GL shader storage buffer. Then down here, this is pretty well unchanged in the demo. We're still using Core 3D. In fact, this is completely unchanged. I didn't even touch this code here from the original demo. And then we have a compute shader. And so the compute shader is made differently. We'll take a quick look at that later. But down here inside the display method, we go ahead and set up the compute shader using this VBO cube vertices, the same array we were setting up before. And here we go ahead and bind it as a GL shader storage buffer. I'll talk about the 0 in a minute. And then we go ahead and run our compute shader. So then later, we go ahead and set up this GL bind buffer, the same one, VBO cube vertices that we had up here. But down here, we're binding it as a GL array buffer, explaining the layout, and then using it to draw vertices in our rendering pipeline. So yeah, the answer to your question is yes. You can use the same buffer on your compute shader that you later use as the vertices for drawing.
You just bind it as a different shape.
Yeah, exactly. Now, in this particular example, it goes ahead and grabs a bunch of data out of it and brings it over to the CPU because I wanted to print it out for debugging purposes. But if you don't pull it to your CPU so you can print it out for debugging purposes, then it'll stay on a GPU. You don't have to bring it back to CPU memory.
So if we pull it to the CPU and don't change it, does GPU copy need updating still?
But if you pull it to the CPU, then you have a separate copy.
Okay, good.
Like this here makes a GL float feedback. If you didn't want to do that, you can actually bind it onto both and use it kind of like you map a network drive. That's an available access mode.
That seems a bit odd.
Well, it isn't. You know, if you wanted to just address some particular element in it, then it might make a lot of sense to set it up like that, and then just change your one element instead of copying the whole thing and then making your change and copying the whole thing back.
Yeah.
So you can change something there that later gets used as the vertices for input. And so that's how this thing's being used. It's being used for both of them. I mentioned I promised to talk about the 0 for a moment. So the GL bind buffer base here, it binds something for your compute shader, but in the compute shader, you actually identify it by number here for this binding. I didn't try taking this back out after I got the whole thing working, and so maybe it's possible to omit it. If you change the number there, like 1 like that, I think that breaks it, yep. And so they do have to actually match. Okay, and if we don't say that at all, it still seems to be finding it. Okay, so if you specify the number, it has to be a match, but if you omit it and the name is correct here, it apparently worked, but we don't actually say what the name is over here. So I think it just looked for the first one and called the first one 0. Or maybe it just defaults all of them to 0. Not sure. Anyway, the ID here though is by index. So if you look up here at the other one, so Chord 3D, we find the attribute location inside the program here for Chord 3D, and then we have this attribute Chord 3D. And then later, when we're going to use a buffer with it, we GL enable vertex attrib array attribute Chord 3D right there, and specify which one inside the program we're using. Here, we just go ahead and GL bind buffer base, and we give it the index. Which should be a match for what it is inside the shader. Okay, so it's bound as a GL shader storage buffer, and it's ready for a compute shader. So we can go ahead and dispatch the compute shader. And the 3 numbers here is the 3D space of shaders that we intend to dispatch. So if we wanted to only operate on one vertex, and we set this to 1, now this is only going to give us one invocation of our compute shader. And you can see there's one vertex, appears to be that one, that's doing the transformation, and none of the rest are doing it.
Wow. Wasn't it 2?
That was 1. Oh, that should have been just one vertex moving. I think it looked like multiple because it was stretching the thing that was connected out there. But yeah. So anyway, 8 vertices. That moves all 8. Okay. Now I mentioned that there's work groups and there's instances and number of instances and things. So it's just kind of a quick exercise in talking about these compute spaces. Let's change that to 1, which breaks our program. And, well, it breaks the program if I actually make it. Okay. You can see it's just moving that one. And so then we'll go ahead and fix it from inside the vertex shader. Okay. Now inside the vertex shader, we've got this local size x equals 1. That's the size of the local work group, the number of invocations inside this work group. So we've got a work group of 1 invocation. So we make it a work group of 8 invocations, and then change this, we should be able to have it. So let me show you the incoming things for this compute shader. Inputs. I mentioned it's stuff to do with the abstract compute space. Yeah, it is. So we were using GL workgroup ID here, which is the ID of which workgroup we are. But now we're just going to have 1 workgroup. And so we're going to go for local invocation ID, and that's which instance we are inside our workgroup. So that was local invocation ID. There we go. Now it is fixed without recompiling. Since we just changed the geometry, so now we're 1 work group of 8 instances instead of 8 work groups of 1 instance. So that's an example of, we really don't need a 3D grid of 3D grids here, and so we're not using anywhere near the complexity that's available to us.
So when would you want to use a 3D grid of 3D grids?
If that makes sense for what you're doing, you know, if you got a 3D grid of, for some reason I'm thinking about a 3D grid of blocks here, and each of the blocks is going to have some complicated operation performed on it that can be multi-threaded and do a few different things. Then you could go ahead and multi-thread it using your 3D space of local instances on a per block basis, and then you can go ahead and do all the blocks in a separate work group.
Well, why wouldn't you want to just throw all the blocks into a 1-dimensional array that's, you know, really, really long?
Well, you certainly can do that if that's how you prefer to think about it. You know, do you index your images by X and Y, or do you just like figure out what offset is by the initial pixel, assuming row major order? You know, you can do either.
Yeah.
And you know, it's one of those things where, you know, somebody could be like, oh, well, a 3D space is really just a whole big long 1D space, so it's just a shortcut in thinking for the weak-minded.
Oh.
But then people would be like, well, unless you forget about some details, then you can think about some different details, and that way you can go further, so you can think about more things. You know, there's arguments to be made for both ways. But if you don't like any of the arguments about the 3D space, just use X or some other axis. Now you might pick Z to be contrary or something. But if you feel like using a 1-dimensional one, you just use one of the dimensions. Okay. So we got work groups and work group ID and local invocation ID. So the number of work groups, notice that these is a vec3 here, vector of unsigns. So 3 unsigned integers. Since the work groups are in a 3D space, you have them specified as a vec3. So you have X, Y, and Z coordinates for your work groups. Same with the work group ID and local invocation ID. And you have a global invocation ID. And so it explains it down here. This value uniquely identifies this particular invocation of the compute shader among all invocations in this compute dispatch call. It's shorthand for the math computation, the workgroup ID times the workgroup size plus the local invocation ID. Basically, if you treat the whole thing as a homogeneous space, then that's the one that you would want. Then you have a local invocation index. And so this is probably something that Jesse would like a lot here. Because this is a 1D version of GL local invocation ID. So if you are really into that, let's not use a 3D space deal, it takes it computes where you are in the 3D space and condenses it down to a number that can be treated as an offset from the start.
So this 3D space thing is just a way of thinking of it.
Yeah,
That it provides for you specifically to think about it.
sure, yeah.
Yeah, okay.
I think they kind of assumed that since it's a graphics card, you're going to be thinking about 3D spaces a lot.
What about 40 spaces? Don't they get a vote?
No, no, they don't. But you could take one of the instance local ones and pretend it's one of those. You can pretend this whole thing is a 6D space if you think about it just right. Okay, and you got local size, yeah. Okay, outputs. Compute shaders do not have output variables. Yeah, you gotta make your own output. Okay, so that's the kind of the way you manipulate those spaces there. Okay, so let's talk about the shader storage buffers a bit and the shader storage buffer specification. So here we have this layout, and so the first thing we have to say about this is which layout we are using and which binding we're using, and I'll go over those in just a moment. Then you have a buffer. So the buffer is as opposed to like in or out or uniform. We have another option there that's buffer.
Why can't we use buffer in the rest of them?
Well, a buffer here means an in-out.
Exactly.
Yeah. Yeah, something like that. Anyway, so a buffer is something that you can use for in and out on these things. So then we have the name outside the program. So if we wanted to go get something out of the program or retrieve something or talk about it somewhere outside the program, we go ahead and use this name. It's the global name for it. So then down here, we can have a local name if we want. So, we can name it something. Ebenezer, that is his name. There we go. So we have now given it a name. See if it still works. Still works. All good.
So when you only have a 1 in there and it just moves one vertex out, can you choose which vertex you move with just the 1?
Like right here?
Well, no, like if you just the local size is just 1, it only moves one vertex.
Oh, yeah, if we set local size to 1, then our maximum GL local invocation ID.x would be 1.
Yeah.
And so we're going to get one instance that moves one vertex.
Yeah, but can you choose which vertex you want to move? Or is it just
Sure. Yeah, because I was using GL local invocation index here to do these things. So if I wanted to do this instead, I could say, go ahead and get rid of that. And let's move vertex number 4. Okay. I think that will just move vertex number 4. There it goes.
There goes vertex number 4.
Yep. Yeah.
Bye, vertex number
So-
4.
Yes? Okay. Yeah, good question. Okay, so the local name down here, you can use it down here. It's kind of like a namespace in a way. So if you go ahead and delete it, and you can see it says undefined variable v. Like what you're talking about, v. Never heard of v. If you just wanted to call it v, you just take out the local name. So there's no local name, and then you just kind of leave the local name blank here too. And now it works again. So the local name is optional, but you might want it because if you've got a number of arrays bound that have kind of a similar thing inside them or similar contents, you might want to name the similar contents the same thing. Like .v is pretty, it's the vertex, right? So if we had like 3 buffers full of vertices, we might want to differentiate them by giving them a different local name right here. So we have to say something .v so we can keep them all, tell them all apart, basically. So that's why there's a local name possibility there. Okay, so that's the contents there, say vec3. Now, you might notice that actually I'm giving it a vec4, and I'm telling it it's a vec3 right here, and there isn't any problem. So this is a memory alignment thing. I mentioned I'd talk about memory alignment at some point. Yeah. So I was trying to pass it a vec3 for a good while, and I still think I should be able to, looking at the documentation, but it sure didn't work. So the layout specifications on this, they're not right under here. Okay, it's on this Chronos. All this stuff is on Chronos. Or it's not that page though. I have all these open in different tabs, and I don't even remember which one's which. Okay, there we go. Memory layout. So we have a few different options. I actually put them in the notes here too. Okay, so there's 4 memory layout qualifiers you can have: shared, packed, STD140, and STD430. I've got this one set on STD430, but the fact is it works no matter which one you pick. I tried each of them. Packed. So these all define how the memory layout is going to be inside this buffer that we're going to access. And so how the memory layout is might affect what our index or brackets do here. We might go somewhere else depending on how the layout is, if there's some change in here. So packed. This means that the implementation determines everything about how the fields are laid out in the block. So the OpenGL API can be used to query the layout for members of a particular block. So the implementation figures it out. And that could be fine, because if you're only going to use this thing in shaders, say you're going to set it up in some compute shader and put a bunch of values into it, then you're going to pull it into a vertex shader. And you're just going to let the implementation figure it out. That's probably fine. But if you're interfacing it with it on your CPU side of the code, you might need to query OpenGL and ask it what it has been doing, you see? So that you manipulate the memory in the correct way. Okay, so each member of a block will have a particular byte offset, which you can use to determine how to upload its data. Also, members of the block can be optimized out, love this one, can be optimized out if they're found by the implementation not to affect the result of the shader. So this is one of those ones that can really get you if you're pulling the contents of the buffer in and out of it and doing stuff with it on the CPU. Because on your CPU side, if you go ahead and read the contents of some buffer, you might expect that it contains members that you put there, even though they could potentially have been optimized out. That said, if they can actually be optimized out and you don't need to access them on the CPU, or you can just plain figure out if they're there somehow, then letting them be optimized out will save some memory. So that's, and I think that's where the packed comes in. It can be the most compact. So you have shared. So shared is more intended for you to be monkeying around with these things on the CPU at the same time as OpenGL is using them. Works like packed with 2 exceptions. First, guarantees all the variables defined in the block are considered active, meaning nothing is optimized out. So if you put some value in there, you can reasonably expect that it's still there. Okay, and second, it guarantees the members in the block will have the same layout as a block definition in another program. So like another shader program. So that could be good too, if you want to share it between shader programs. So long as the blocks of different programs use the exact same block definition. So you got to define it the same way. Be careful of specifying default matrix storage order. You can change your matrix storage order between row major and column major. Because that can implicitly change the definition of blocks, sure. And finally, all members of the block have to use explicit sizes for arrays. If you just leave the empty braces and you know it's going to be some array, if you want to share it between them, you should actually say how big it is. I like this optimized out stuff. It actually has legal precedent. For example, if you have a house and it has a property line, and you build a fence that's 10 feet on your side of the line, and then you sell the house and somebody else owns it, and you sell the house and same thing happens next door. Eventually, you know, the effective property line has been moved, and then if you go to court about trying to get your property line back, it can be taken away. So your property has been optimized out because you didn't use it. Okay. It's called adverse possession in real estate. Here, it's just called optimized out. I'm not sure if any of these examples actually bring anything to light. Okay. But they may encourage building fences along property lines, potentially. My mother-in-law has just done this. I did mention this to her, but she has just built a fence like 10 feet inside her property line.
If it doesn't, it's the next person that's going to get that.
Yeah, there's usually a time period. It's usually like a decade or something.
But besides, you have a 10-foot boundary to your property line anyway, that you can't build any real structures.
It depends which property line, and which state and county and things like that.
So why not put it in fence?
See, that's the thing is, in a lot of places, fence isn't considered a structure.
Right.
Exactly.
And so if you
This
move the
way-
property line closer, it limits where you can build structures.
This way you can build your shed right on your new fence.
Right.
And
I like how building laws are just as convoluted and weird as any kind of programming system you can come up with.
Oh, yeah.
Oh, yeah.
And then there's tax law.
Oh, yeah.
Let's not.
So,
talk about that.
Tax law makes compilers.
with these ones, so so you can use a shared if you want to share things between things. So basically, packed is best if you're kind of using it within one shader or one shader type or whatnot. Shared is a lot more guaranteed to work other places. So then you've got STD 140 and 430. So STD 140 alleviates the need to query the offset for definitions because there's rules for STD 140 layout that state the layout arrangement of any interface block declared within this layout. So you can share this across programs since there is a standard layout. The only downside of this layout type is that the rules for packing elements into arrays and structs can introduce a lot of unnecessary padding, which of course wastes space. So the rules for STD 140 layout are covered quite well in the OpenGL specification for OpenGL 4.5, section 7.6.2.2, page 137. Standard uniform block layout. There's the official definition. We won't dive into it right now, but the point of this STD 140 is to give you a standard one where nothing's getting optimized out, and you can kind of guarantee a certain layout. Now, warning, implementations sometimes get the STD 140 layout wrong for Vec3 components,
Of course they do.
just so you know. Okay, then you have STD 430. That works like STD 140, except with a few optimizations in the alignment and strides for arrays and structs of scalars and vector elements. Specifically, they are no longer rounded up to a multiple of 16 bytes. So an array of floats will match with a C++ array of floats.
That's a good thing, right?
Yeah. So this layout can only be used with shader storage blocks, not uniform blocks. Now the reason I was using STD 430, I was trying to use something that was not a multiple of 16 bytes. If you have a vec4 of floats, 4 bytes per float, so your vec4 of floats is 16 bytes. I wanted to use a vec3 of floats. Couldn't get it to work, even with STD 430.
Oh.
So I might be interpreting this wrong. It might be that I'm looking at this and seeing that it says they're no longer rounded up to multiple of 16 bytes, so therefore my vec3 is fine. But perhaps what we mean here is that arrays and structs are no longer rounded up to a multiple of 16 bytes. Not the vec3s are not rounded up to a vec4. You see? It doesn't quite exactly say it. I did go read OpenGL for this thing here. If I had, I'd probably know. So vec4 was seems to be where it's rounded up to. Now, computers are always having alignment issues like this. I think I showed my operating systems class, which probably includes like everybody here, about that kind of recently actually with struct packing, and actually with networks class we talked about struct packing
I
too.
remember that.
Yeah, so alignment pervades computer science. It's available all kinds of places. But anyway, happens here too. Sure.
Alignment's,
Yeah. Okay. So the alignment here is set on 16 bytes, and so this vec3 here doesn't seem to affect anything. I should probably say vec4 just to be clear about everything, but it's right now it says vec3. If it says vec4, I don't think it'll change anything. No, works the same. Cool.
so can you pass a vec4 to something that takes 4 floats?
Sure.
And have it automatically unpacked into those floats?
Well, they'll be automatically unpacked in the sense you can say your vec4.xyzo or RGBA or whatever.
Well, I was meaning the function itself is defined as float. And you give it a vec4.
Oh yeah, I think you can. Because for example, if you have a function called like normalize and you give it a vec3, it works as 3 floats. And if you give it a vec3 comma another value, then it takes it as though we're a vec4. Maybe normalize doesn't. Vec4 creator does. I'm not sure how they define it actually. In a lot of cases that seems to work. Okay, so there's kind of the way shaders storage buffer. Okay, so layout specification, sure. Favors alignment on 4 floats, 128-bit lines. Couldn't dissuade my drivers from doing that. Binding number, showed you binding number earlier. Okay, so yeah, we went through the compute space. Okay, so there's our complete example. So things I kind of glossed over. First of all, you have to attach your compute shader to a different program. So I've got this separate program down here, C program for the compute program. That's GL create program. If you go ahead and do this and attach it up here, you'll get a message about it. Not C program, I'm trying to attach it to a regular program. Okay, so it gives me this link info. Programs may not contain both a compute and a non-compute shader. So, now you know. Okay, simple and definitive. So you do have to make a separate program for your compute shader. And so you have to go through the usual set of work here where you make a program and then attach your shader to the program and then link the program. And then we can see if it actually built okay, which is kind of nice to know. And so then we can have a separate program. Building a compute shader, it's really just the same as anything else. If you're doing a tutorial code here, you can use create shader. Remember, create shader is something that the tutorial came with, and we keep using it again and again and again. But actually, it runs a bunch of GL functions under the hood.
Doesn't it just import a string file?
It's in shader utils. So this is create shader. And so it, it reads in from the file and it calls GL create shader with the type that we wanted. And then it builds the source by taking out the stuff in the file and putting in some other things potentially. And then it says GL shader source with the source. And then it does GL compile shader to actually build the shader. And then if that worked right, it returns it. Otherwise, it prints out our error message and calls GL delete shader and gets rid of the shader that didn't work.
So why is it taking out so much stuff?
Taking out so much stuff?
Yeah, like ignore GLSL 2 precision specifiers.
Oh. Well, for fragment shaders only, it looks like.
What about the one on the bottom there?
This is only for OpenGL ES, this part.
Oh,
So it's trying to support OpenGL ES, which we haven't used at all. In fact, we haven't even updated. We're using this version for OpenGL ES, and that's actually OpenGL like 4.5. Okay. So then this so then for actually running it, kind of went through this before. Basically, we're running our compute shader up here and dispatching it. I guess we're dispatching one work group now, but the work group has 8 invocations, 1 to move each vertex, and so off everything goes. Works pretty good. Okay, so the bind buffer base binds our buffer there. And then eventually we have this GL memory barrier. And I think it works okay without it, although I've left it in. Yeah, it works fine. But here's the reason for it. And it's better practice to leave this in here. So when we're dispatching a bunch of shaders, OpenGL is going to get going on running the shaders. Now, it's not actually guaranteed that they're finished after that line, which is fine. If you think about the regular OpenGL rendering pipeline and GL flush, we used GL flush the other day to make sure our computation was finished. GL flush actually executes any rendering commands that are left. So GL memory barrier does something similar here. We're setting a memory barrier for the GL shader storage and waiting until it's actually done before we go and try and use the results from it. So you do need to watch out for potentially running on afterwards. Now, I just showed you if I comment this out, the program actually works just fine. And in a lot of cases, they will work just fine. But you do think about synchronization issues here if you're running something and then using the results of it immediately afterwards. You don't want to introduce like a weird rare bug that you don't see it that breaks your program later. So then pulling the stuff out of this. I've got this feedback array, and it automatically adapts to the size of the array. So if we set that at 10, for example, and make this and run it, we only get 10 items along here. This is the coordinates being pulled back out of the array. And we actually don't necessarily need to do this. I was doing it partly to leave a demo of how and partly to see what was going on when it wasn't working. So we have the feedback array here of 10 floats. And then we'll go ahead and get the, we'll go ahead and fill this from our shader storage buffer. So size of here is actually going to return 40 in this particular case, 4 bytes per float. And so we're going to get 40 bytes out of this storage buffer and put it in feedback. So then once we got this loop here, since the code was carefully designed to operate based on the size of the feedback here, I went ahead and set up a loop to also operate based on the size of this feedback array. It does mean that you can't define the feedback array on the heap. If we made this with malloc, this would run the wrong number of times. The way it's set up here, I take the size of feedback, that's 40, divide it by the size of a float, that's 4, and so you get 10. That's the number of times we wanted to run. So when you add that on the feedback, C actually adds 40. Because when you add a number to a memory address, C will add the right number of addresses for your variable type. So if you add 10 to the address of a float, it actually adds 40 bytes because floats are 4 bytes each. So it's like feedback plus 10 floats. So this division here figures out how many floats are in the array. And then this plus here adds on the correct number of bytes for that many floats. I realize that this sounds like we did something and then undid it, because that's exactly what we did. The other way we could have done this is like cast feedback as a void star or char star, and then go ahead and add on the size of feedback, 40 bytes, and that would work as well. Okay, and so let me just increase I there. So I is a pointer to the float we're currently on, and so when we say plus plus I, we're adding on 4 bytes, like we're adding on 1 float to that memory address, the address of the float, and then we print out the float right down here. Okay, and yeah, run on new line afterwards. Okay, so I get stuff back out of it. So then we go ahead and enable our next program, and then all this stuff is just like before. The only thing is, since I'm using a vec4 now for each vertex, I had to change this to 4 instead of 3. So that stuff runs just like usual. Sorry, I'm tired because I slept a long time last night for the first time in a while. So now my body's like, sleep, remember this stuff.
Sleep is nice.
That's actually, I think they did a study on that. People who sleep deprived often, it's like their body gets bad at knowing when they're tired.
Yeah, yeah. It was my daughter was waking up early, like just after 6, and I could go into bed late, and then I was sick. So normally I was getting like 6 hours of sleep, which is normally about fine for me. But when I'm sick, I need more than that. And that was like 2 weeks ago. I was sick, but for some reason things just haven't returned back to normal yet. Okay, so that's a compute shader example, simple compute shader example. Okay, so we can get it out there. So that means we could actually use this for general purpose computation if we wanted to. Let's go ahead and do that just real quick here. Suppose that we just decide to end our whole thing right here and not actually render anything. So we'll just say return, and the compiler might complain about that, but it'll be okay if it does. So then we got our vertexes set up here. So let's go ahead and not do that. Let's duplicate this whole thing here because we're about to do general purpose computation. And so then we'll comment out the original because we might want it back in a moment. And so away goes this one. Okay, so then instead of doing this, we'll just say like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then all this stuff can go away. Okay, so we got an array of 10 floats right here. And so we went ahead and GL gen buffered, and we put the right size there. So I think that's actually probably all right. So then our compute shader, we'll go ahead and say instead of vec4, this is just floats. Okay, and these will be numbers. Okay, and then down here, instead of doing this stuff, We want a local size that's bigger than 8 too. We want a local size of 10. We put 10 floats in here. Okay. So then we can say something like nums at position, geolocal invocation id.x, and we'll make it equal to sign of what it did before. Sign the square root. Square root of what it did before. Okay. Nums at position, geolocal invocation id.x. Okay. So we'll assume it's an array of floats, and for each of the floats, we'll go ahead and calculate its square root and replace it with its own square root. Okay. Oh, I must have done that wrong. Geolocal invocation ID was not that. Geolocal, oh, underscore. That's what I forgot. Okay. Okay, something went wrong here. I actually don't have any control over this window anymore. I can make other windows. I can switch to that one, but nothing comes up. Kill all. Lots of L's in kill all. Terminated. Okay. So it doesn't appear to have actually changed them.
I just feel on 1.0.
I would say I made a mistake. Okay, so we started a rendering loop that just returns and doesn't render anything. I wonder if that's a problem.
Probably.
Evidence here indicates that it might be a problem.
Looks like a problem.
We could just run it once instead.
That or it's done.
A duck.
I didn't think about that being a problem. Yeah, it's definitely a problem. Okay.
Looks like that.
So we'll go ahead and idle plunk it and put display function in it, and we'll just run it. Run it once. And we won't actually let main loop. There we go. There's the square roots of each of those numbers. So now we've got a general purpose program that uses OpenGL to calculate the square roots of 10 numbers.
It seems so very pointless.
When you say
Well,
that now.
I mean, it's about as pointless as the suggestion I made earlier, so.
It is. But this one does 10 at once. Doesn't that mean this is like 10 times as good as your suggestion?
I don't know, maybe.
Okay. So this is, it's a little bit ridiculous. I wanted to show you that the compute shaders can actually be used for general, just computation. It works.
Isn't that what compute means?
Yeah, it is. Yeah. Well, but sometimes words mean different things than you might think they mean in programs. We mean something very different than a biology major when we say tree. Okay, so let's go ahead and put these things back together the way they used to be. But now you know that it can be done, and so if you ever are inspired to do it, you will know that you can do it. Okay. On display has a return in the middle if it's need, and I think we're about there. Feedback just took the first 10 things out anyway. That stuff's all fine, so it's just the shader is all wonky. Okay. Oh, that's what happens if you replace some of the values with their square roots. Oh, they came out as not a number. Because we took a square root of -1.
Good job. I'm so happy for you.
Okay.
Why?
So we can transform them in some more orderly way. Now, right now, we've got these as an array of floats on a cube. And so here's an example of something that we could actually do. We've got local size set up as 10. Now, the actual local size of this thing, we got 8 vertices, and they each have 3 components. So there's actually 24 floats. Let me go ahead and make each of them bigger. Nums at position, GL local invocation id.x times equals 0.1. That should make a cube that grows. That did not make a cube that grows.
Aren't there four vertices? You changed the 43 to 4 vertices.
You're right, I did. That can make a difference. And the last one is the W position. So actually, we might get something still weird because we're changing that one. We should probably suppress changing that one. So we made them all 0. They increase in life. I'll have to win. Well, that makes sense. We have to multiply it by something that's bigger than 1 to make it bigger. Otherwise, we shrink it down into nothingness. Yeah.
Well, that just explodes, doesn't it?
Yeah, it's a very fast. That's the kind of cube you kind of want to take a step back from. Step back. That's right here, this row. So we step back a bit. Yeah, it goes really fast.
Maybe you think it's cereal.
Yeah. Oops. There you go. Okay. So you can do this thing as a nums there. Now, here's an interesting quirk of doing it this way. So when we were doing it per vertex, we had 8 total invocations, once per vertex. Now that we're doing it once per coordinate, and we've got 4 coordinates per vertex, we actually have 32 invocations. So by doing this way, we have managed to increase our utilization of the video card.
But not our performance.
They very well perform faster. The video cards are very well adapted to produce, to do very short processes a very large number of times. And so we've got a shorter process that happens more times now. So it should be more favorable to the video card.
If you could find a way to make it work 100 and some odd times, it would work even faster.
Like each of them multiplies like half the floating point number or something? Yeah. If we think about that long enough and it CS 250 cents, we might actually figure out how. The concern is that there might be an overflow depending on how it was done. And so if there's an overflow, then they have to communicate with each other. And if they have to communicate, that's going to slow everything down. If you watch,
just have to have a go-between.
right. It's like if you watch an Olympic bobsled team, they don't stop and talk about what to do after the clock goes off.
So if you make that number that it's multiplying it by smaller, like still bigger than 1 but smaller than it is, would it slow down the process?
Yeah.
That's much nicer.
It looks like it's coming, but it's not. It's just getting bigger.
It looks like it's attacking us.
Yeah, like the border coming, the rainbow board.
Rainbow board. Teapots are harder to render with this, I think.
Maybe.
So,
Because we don't have the teapot function.
Well,
how is it more efficient that we're using more more processors per point?
well, if we were to do this with each vertex, we'd have to. So let's just change it real quick here, and then maybe we'll make a teapot enough. Okay, so let's change this to 8, and then instead of nums here, we'll say that this is a vec4. And so I don't think we actually have to change a thing. I think it'll still work. Same effect. But what we're doing now is instead of doing each of the components on a separate one, we're using 8 threads. But when we say this times equals here, we're actually specifying a vector operation. So this is entirely hardware dependent. If each of these compute shaders, and they very, very well may be able to, I haven't really looked at the hardware capabilities that much on this stuff. If each of them can do a vector multiplication in a single cycle, then it doesn't help us to break it into 32 of them. However, if they can't, if they're essentially multiplying each of the 3 components in sequence, then it does help us.
Right.
Okay. So there was that. Oh yeah, and Alex misses teapots.
Yeah, I miss teapots too.
I don't remember exactly how you
I
do
think
this.
everybody misses teapots to some degree.
That's why they included them as a primitive.
There it is.
Yeah. We could make it bigger. Is that the size?
Yeah.
Yeah, it's getting absorbed by our box. But if we wait until we're inside the box, we can see the teapot.
That's a pretty teapot. Why isn't the teapot drawn?
Why isn't it what?
Why isn't the teapot drawn?
Because we're not applying our program to it.
Oh.
We're just drawing it in the standard way. There's probably some way to extract the teapot model from Glut. I don't know what it is.
Wouldn't the graphics card automatically have it?
Well, it gets into our video memory in some way. It's probably possible to extract it.
Yeah, so can't we just say, here, graphics card, take this primitive I just tried to draw. Compute away.
What if we did this? Instead of saying GL draw elements, we'll not say that. We'll go ahead and, no, that's not gonna work. I was gonna say we just draw teapot instead and see if our program gets applied to it somehow. But we didn't bother to tell the program about the vertex attributes arrays or where any of that stuff is, so I don't think that would probably work. All right, now since Glut is open source, free Glut at least, we can probably grab the vertex array out of the library and just draw it. Okay, so compute shader, yeah, we can do that. I had some other idea for what to do with the compute shader in order to finish the demo. Oh yeah, so we can also use these things for physics if we wanted to. So in order to use these things for physics, we kind of have to keep track of where they are at any given point. And we have that. And we have to keep track of their velocity and what acceleration we want the pieces to be subject to. What we'd have to do is set up another array, but it would only have to be an array for our compute shader that has the velocities of each of these things. So up here, we went ahead and made this buffer right here. We GL gen buffered, and we actually got our buffer. Go ahead and grab that and make another one. Okay. And so we've got these cube vertices and whatnot. Now we can simplify this a lot. So let's go ahead and say we want to GL do this, and this is going to be cube the vertex velocity, VBO vertex velocity. That'd be good. Okay, we'll do a shader storage buffer. We call vertex velocity. Okay, it'll be the size that it is. So that would be, well, we could also just figure out, we can also just leave it that way, because that's actually the size it is. But that's not the data we want to put into here. Fact is, what we want to put in is just initialize them to null. But I think we're going to have to do that. There might be a way to initialize to null. I know if you leave this out, it's okay, but it won't initialize them. The contents are undefined. And so that's not the same thing as initializing them in the slightest. We could use a compute shader pass to initialize them, but that seems to be a little bit more work than one quite needs to do. That said, it would avoid the transfer through the PCI Express bus.
Oh.
But the other way to do this is just make them all zeros. So those become 0. Those become 0. Some of those become -0. I wonder if that's a problem. These become 0. Sorry, it's a little bit tedious. Okay. So now we've got zeros going in all these things in the vertex velocity array. So we have a vertex velocity, one of these. By the way, so our specification here, static draw, has actually become quite inappropriate. I'll leave it there for the moment, but it would be nice of us to not be misleading OpenGL about how we intend to use this thing, which we presently are. Okay, so then down here, there's nothing really about the array in our create program. We just go ahead and make this program and link it and all that sort of stuff. Then down here, when we bind buffers, we said GL bind buffer base. We got to go ahead and bind 2 buffers. This This will be index 1, and what do we call it? We remember
Vertex velocity?
yeah, VBO vertex velocity, but we forgot to actually make a global for that. So we need to do that up here, same way as that other one. Okay, so I think that takes care of getting it into the program, and so then we can go ahead and dispatch compute shaders. Sure. Okay, so and then over in our compute shader, .c.glsl, we can go ahead and duplicate our little layout block here. And I don't think we want to really call it nums on both of these things. In fact, this one might be good as vertices, and the other one would be velocities, which also starts with V, so we can't do that. Let's call this one vertex, and this one velocity. Okay. So then we can do a little physics simulation here just fine. So we got our velocities. Now, it might be nice if the initial velocities were set to something, actually, come to think of it. I think we might do that in a moment. But for starters, let's just say the y part's going to fall. So we'll say velocity at our position. We're still using this local layout here. And we'll say the y component of this one loses a little, or we got to decide which way it goes. If positive y velocity is down or up. Let's say negative y is down, like negative velocity is down. So we'll say it loses a little bit, 0.01. That's not very much. So that would be gravity there. So then we go ahead and transform our location. Vertex plus equals velocity. But we have to say which invocation ID we're talking about. This is where we start to do and not appreciate these long names. They're trying to make it clear, so you don't have all these little variables that are named X or A or B or whatever. Okay, so we should be applying our velocity there. Now, this will make the whole cube fall. If we do this right. Cube vertices is redeclared. That would be up here. We had cube vertices, and then we made another one that was also called cube vertices. I'll call this velocities. And I'll call it vertex velocity down there. Okay. Okay. Different buffer variables sharing the same offset within a storage block. So, yes, I said binding is 0 for both of them. That is not something we do.
Oh, are you building a structure? Or something?
Different buffer variables sharing still. Same chord 3. Oh, same chord 3D both times.
Okay, good.
Okay, it went somewhere. I don't think it went quite the right place. Let's slow this thing down and see. Let's slow it down more. How fast are we going? What if we comment that out? There's something else going on here. Like this velocity already set to something when we start this. Yeah, something like that. Now we don't have any name. Okay, so it's definitely that line. So I would say that velocity is not set to 0 when this whole thing starts. So that probably means a mistake in here. If we take a look at the spot down here where we made this, you can see that we actually found VBO cube vertices as both vertices, vertex arrays. So that should help. Oops. Okay, now it's static despite the compute shader's best efforts, so we'll go ahead and put in the following.
Wow.
Okay, So we made it full, so we've got a physics simulation there going. But our physics simulation is on a per vertex basis.
Uh-oh.
So that means that the vertices don't actually have to fall at the same speed. In fact, they could also hit a floor. And so if we edit this thing to add a floor, we can say if, let's say we drop this thing to about -5. So we'll say vertex geolocal invocation ID dot x dot y. So if our location is less than -5, then we'll go ahead and reverse our direction. Y, say times equals -1. That's a good way to reverse direction without having to type geolocal invocation ID again. And let's see what happens. Since the two are bouncing independently, the top and the bottom, you can see that chaos ensues until it gets stuck in the floor. I've done quite a few bouncing and physics simulations in like CS 108 and other classes, but I've never quite had one like this.
That is really nice.
Since the floor bounces through the top of it at times.
Oh, what's it doing now?
It's getting stuck in the floor.
So how come it becomes a cube again instead of a flat pancake?
Because only part of it's getting stuck in the floor.
See the top of it's still bouncing? And I think eventually, so the part that's stuck in the floor is actually making slow progress downwards.
Oh.
We can prevent it from getting stuck in the floor. We just have to move back up where it belongs. We'll say vertex local invocation ID dot x dot y equals -5. And that'll put it set back on the floor. But since we've actually given it a little momentum, like it's sunk into the floor, the reverse of the velocity is set onto the floor, thus elevating it and adding to its total energy. We're going to see that it actually continues to bounce higher.
I love that thing.
They bounce at a little different rate too, because they started out at different heights, the top and the bottom.
Mm-hmm. Oh, that thing is beautiful.
Okay, we'll make it one weirder still. We'll go ahead and return just a little more energy than it lost. Maybe we should do more energy and make the effect more obvious. It'll take a good, because it only does it per bounce, so it'll take quite a few bounces before it builds very much up. Yeah, they are. Anyway, so compute shaders enable all manner of silliness. Okay. So there's a physics demo inside a cube shader, or a compute shader. Okay, I forgot to add a practice problem to today's notes. I just started doing this, and so I'm probably going to forget a lot of the time for a while. So go ahead and add one. Okay. Practice problem. Add some velocity to the x or z direction for the cube vertices by making them the same and different. Okay. And I think the compute shader is already set up to handle that because if we look at this cube shader in here, we're actually applying the whole velocity vector, not just the line component. So I think if you were to set something, I won't do the whole practice problem, but if you were to just change one of these velocities here in x or z to like 0.1, you should actually see an effect.
That's what I'm worried about. What exactly is it doing? It appears to be sort of rotating on.
Well, it's going further out, but then the rotation's being applied after it moves out. And so that's why it's coming, it's going further away from the merry-go-round. Yeah.
I see. So,
So if you change all of them, you get the whole cube bouncing around. But if you change it differently, it'll change the cube's geometry as it goes.
it would.
Yeah. Okay. I'm going to go ahead and copy this to the. I saw it for two.
And to prevent the top from bouncing through the bottom.
You could do that. The first four are part of the top. The second four are not. And so you can go ahead and add an if statement to C, and you can bounce them against each other, or just not let it go through, or something like that. Bouncing them against each other might be the most amusing.
Or you could use your three-dimensional array and not bother with it.
Yeah. Oh yeah, that's true. Because you could figure out which ones are which by using the three-dimensional array. Because you can have all the ones for the top one in one, and all the ones for the bottom one in another. And so then you could just set the bounce plane for the top one as wherever the bottom happens to be.
Yeah.
Yeah. That could totally work. Okay, the demo's uploaded. Okay, well, I will see everybody next time. Have a nice afternoon.
So with my hair,
Yeah.
could I feed in the coordinates, the former coordinates of the hair to the vertex shape? I've been calculating